this lecture is going to focus about the reflection from a metallic surface. Now for a metallic surface, we already know that epsilon 2 is going to be a complex thing, as we had seen a few lectures ago. So what would be the form of this? It's going to be epsilon 2, which is the real part, plus I times 4 pi sigma 2 upon omega. And also this 4 pi sigma 2 is going to be much larger than the omega epsilon 2. Okay, so with these sorts of things, we already know that the refractive index, which is root epsilon 2, that would transform to epsilon 2 tilde, and that would be this. And because of this particular limit, this could be approximated as I 4 pi sigma 2 upon omega, or that could also be written as 1 over 1 plus I, according to what we had discussed before, C by delta omega 1 plus I, or that could also be written as lambda bar by delta 1 plus I. So let me write this equation number 1, where we have used. So what did we use? We used number 1, root I to be equal to 1 plus I by 2, as we already know that this is e to the power I by 2, and then the square root of pi by 2 is e to the power I pi by 4, which is just this. And then we had used delta, which is the skin depth, which is just root 2 pi sigma rho c by root of pi to sigma omega. And then the third thing that we use is the lambda bar. Okay, so lambda bar is basically a reduced wavelength, which is c by omega, and that could also be written as basically this is c by omega. So if we check, so this is just lambda bar by delta. We could also check from here that this is going to be c by omega delta, and if I put the value of delta over here, we will get root. So this is c by, so this is c by omega root 2 pi sigma, so this is going to be root c by root 2 pi sigma omega. So therefore, what we will get, so omega, so this is root 2 pi omega is essentially, so this you could get mu by sigma, because omega is what? Omega is 2 pi nu. So that would give us basically, so this is going to be omega by 2 pi sigma. So this is also 2 pi nu. So this is 2 pi nu, 2 pi root square, and that cancels with root. And so therefore we will have omega, c cancels, nu by sigma is surviving. Okay, so now therefore let's write what should the value of the amplitude for the reflected wave should be. So this was E1 naught. So what we had was N2 minus N1 upon N2 plus N1, and then E naught naught. But however, this has become N2 naught. So this is going to be something like this. Similarly, we will have E2 naught, which is going to be N2 naught, 2 in N1 in fact, upon N2 naught plus N1 E naught naught. Okay, so now we will just put the values into these equations. So this was my 3.1, say this is 3.2. So 3 point, using 1 in 3, we obtain, what do we obtain is this, E1 naught is equal to N2 minus N1. So we will have N2 is basically lambda bar by delta 1 plus I and minus N1. upon lambda bar by delta 1 plus I plus N1, or this is going to be 1 plus I, 1 plus I, or basically 1 minus N1 delta by lambda bar. If you wish, we are just multiplying by delta by lambda bar on both the things. So we will get plus 1. Similarly, here we will get 1 plus delta by lambda bar minus 1. It's going to be plus I, in fact, and this 2 is going to be plus I. I'm just writing the other term other way around. So now we will just take the magnitude of these things and in fact square of this, okay, or rather we could just write R, which is going to be the reflectivity or reflection coefficient. That's going to be 1 naught square by E naught square, so that's going to be square of complex square, in fact absolute of this, so that's going to be whole square minus 1 plus 1, in fact I square is plus 1, and similarly here you will have lambda bar square plus 1. So now what I will do, I'll just consider the case. So this is basically delta by lambda. Delta by lambda is going to be very small because sigma is very large. So this is 4. So for large conductivity, delta by lambda, which is root mu by sigma, as sigma 2 is very, very large, as sigma 2 is very high. So therefore, delta by lambda bar is going to be much smaller than 1. So therefore, we will use the binomial theorem to expand these things, and what we will get is just the first term. So that's going to get us 1 minus 2n1 by n1 delta by lambda. So that's going to get us 1 minus delta by lambda n1, 1 minus 2 n1 delta by lambda plus 1. So this is 1 plus x, I'm sorry, so this is going to give you 1 minus n1 by lambda, 1 plus n by lambda. So we will take the inverse of this, expand these two things binomial. So we will have 1 minus n1 delta by lambda, 1 minus n1 delta by lambda. So we will get 1 minus 2n1 delta by lambda. So that's going to be an approximate thing, and which is approximately sort of 1, and t is essentially r minus 1 minus r. So that means that's going to be approximately equal to 2n1 delta by lambda. So this is near 0. So what does it mean? This again confirms that our in fact, we could just put the values as well. So what was this? This is mu by sigma, and this is 1 minus 2 and 1 root mu by sigma 2. So this again confirms that the reflected wave is just going to be very large. In fact, it's going to be a totally wave is going to be fully sort of reflected. So that means wave is fully reflected. So just to give you some picture, so this is what we are going to get. Suppose we had started with a wave like this. Let's say this is the wave, that's the incident wave. So what we will get? We will basically have the wave fully reflected back. So that means we could in fact have something like this. So that means we will have stand waves. Okay. So this is the reflected wave. So that means stand wave solution. Okay, so that reflection should in fact occur over here, and of course we will have a tiny amount of the wave that is leaked out, so that will die. In fact, that will get attenuated slowly and it will die. Okay, so that's transmitted. So let me just finalize what I said just before a few seconds ago. So what we have, remember, E naught. E naught was Ex hat, then we had E naught naught e to the power I k1z minus omega t. So that's what we had taken before. So therefore E1 is going to be Ex naught. Of course we will have a negative sign. E naught naught naught, that's going to be E1 naught. So this is going to be E1, and in fact this is also going to be approximately equal to E1 naught e to the power I minus k1z minus omega t. So therefore totally, which is just shown over here, is going to be E1 plus. So that is what we will have into a medium. So that's going to be Ex hat E naught naught approximately equal in fact e to the power I k1z minus e to the power I k1z e to the power minus I omega t, which approximates to e to Ex hat 2 e naught naught sine k1z e to the power minus I omega t. So that is the kind of amplitude we have for this particular wave. So obviously this tells by how much factor the wave will get attenuated at. Okay. So obviously this gives you some idea why the conductors don't transmit any. The metallic surfaces do not transmit any electricity. Okay, so no chances of leakage. That's what it says from the surface of a metallic conductor. So that in fact tells that metallic conductors are good for the for the propagation, for retaining E without practically no transmission. Well, you already know what do I mean by the no transmission. Okay, so this at least completes the applications of the Fresnel's equation that we had been discussing in the previous few lectures. From the next lectures onwards, we will be discussing the electron propagation of electromagnetic waves into the ionosphere and into the plasma, but that would come a bit later. For now, I will say stay safe and keep learning as much as possible. Thanks.